one question in your exam is going to be about a titration and the sketching of a titration curve to show what's happening at different volumes of the stuff being added from the burette. So I'm going to use this example here, 0.500 moles per litre of sodium hydroxide being added to 20.0 mils of 0.250 moles per litre ethanoic acid. So just so you can imagine what would have happened, a 20 ml pipette would have been used to take an aliquot, 20 ml aliquot of ethanoic acid and put it into a Erlenmeyer or conical flask. Right. Then a couple of drops of indicator. I'm not going to tell you which one in this case yet, because that's going to be part of what I hope to teach you here, how we choose which indicator to use. So an indicator would be added, that would be put under the burette. In the burette would be a standard solution, or standardised solution of sodium hydroxide, and that would be added. The indicator would change colour when this has got to what we call an equivalence point. Equivalence point means same. Okay, so the equivalence point is when there's the same amount of each, pretty much. So it's where it's neutralised. Okay, just be aware that neutralisation doesn't mean a pH of 7. It means that the equation for this has gone to completion. All right. So the equivalence point is where the number of moles of acid equal the number of moles of base, same amount of each. The equation for this is just putting the two together. NaOH plus CH3COOH goes to, it's not an equilibrium, this is a full reaction, sodium ethanoate plus water. Hence why it's called neutralisation, water is a product. Now these are going to go on to react with each other, and we should know by now that ethanolates are alkaline salts. So the pH of this is going to be above 7 when this is happening. The analysis of this equivalence point pH is something we're going to have to do today. There's another thing you need to know though, and that's a thing called the endpoint. And the endpoint is just subtly different. Right? The endpoint is when you see a change in the indicator. All right? So just be aware, equivalence point and endpoint are not quite the same. So that's, the endpoint is when you get a change in colour due to the indicator that we choose. Okay? And we'll choose one today for this. Okay, so you need to be able to calculate the equivalence point, pH and volume for this experiment and plot that on a graph. You actually need to be able to do the pH as well, but we'll get to that later because you can actually just estimate that at the moment. You also should, from the data given, know what pH it will head towards when we go past the equivalence point. Right? And there's another couple of other points in here. So, what we're going to be looking for is a starting pH, so pH that the acid is at in our Erlenmeyer flask. So we're going to have a starting pH. Alright, so we'll call that A, point A that we're going to calculate. We're going to have a thing called a buffer region, which is going to be somewhere around here. Okay, we'll call that B. You're going to have an equivalence point volume. We'll call that C. And you're going to have a pH that this will approach but never reach. And we'll call that D. Put all these together and we'll get a general shape of a graph that looks something like this. And initially, when I add a bit of the sodium hydroxide to the ethanoic acid, it initially will start to neutralise quite a lot of it. So it'll initially raise the pH quite dramatically. Then it creates a buffer region. We just did some work on buffers. Buffers don't allow much of a change of pH at all. So enter a thing called a buffer region where the pH hardly changes at all, despite a large increase in volume of sodium hydroxide. Then suddenly, the buffer isn't effective against a base anymore. So it dramatically changes pH and then approaches D. And if I've done my sketch correctly, which it looks like I haven't quite, but it's close enough, the steepest part of, I was close, the steepest part of that sudden change in pH will be our equivalence point. So I'm just going to move that, and it'll be a little bit of a cheat. Right, move C to there. So we need to be able to find these things and sketch a general shape. Sketching the general shape, so going up into a buffer region, then dramatically going up to approaching a pH, is an achievement criterion. Calculating D and calculating C are achievement criteria. Calculating A and B are required for merit, although actually B's pretty easy as well. It's also what we call a half equivalence point. So it'll be half of C. Okay. This half equivalence point. So that's all sort of your merit criteria. It used to be in the old standard. To calculate the pH, not just estimate, but calculate the pH at the equivalence point, so this point here, which I'll call E, quite appropriately, is what you need to be able to do for excellence. Right, so that's our hardest thing. And I may not cover that one in this video, I might do that as a separate one. We'll see how we go for time. Right, so let's hit the achievement stuff first, because that's what we all should be able to do. And the first one I'm actually going to do is D, because I actually reckon that's the easiest one to plot. D is basically the it's basically the pH of the base being added. Because once I've neutralised and I keep adding that base, it's going to get closer and closer to the pH of that base, isn't it? Hopefully that's common sense. So to work out D should be quite easy. I need to know pH. Well, how do I find the pH of a base? There's two ways to do it. I can do POH and then go 14 minus that. Or I can go KW, so 10 to the negative 14, divided by the concentration of the base. Then that will give me hydronium ion concentration, and do negative log of that. I'm a bit lazier. I like to do the POH way. So I'm going to go, oops, sorry, change the colour there, that the POH of this base is the negative log of 0.500. Alright, so negative log 0.500 is 0.301. Which means that my pH is 14 minus that. Because that's 14 is POH. And so I get 13.7 to three significant figures. So therefore I can put that on this graph. And I've got my first achievement criteria done. So all that is finding the pH of the strong base. Now if it was a strong acid being added to a weak base, so the shape would be the opposite, drop suddenly buffer region and then come down here, which we'll do later, then of course it would be even easier to work out because it's just the pH of that acid.
What was that other way that you mentioned that you could work out?
Oh, thank you for reminding me. Yes. So the other way I could have done the same calculation is to go hydronium ions are equal to Kw over hydroxides. So because there's only one hydroxide in that, sorry, something I should have mentioned before, then I just go 10 to the negative 14 divided by that, so divided by 0.5, and then that'll give me my hydronium ion concentration and go negative log of the answer. Thank you, I forgot to mention that. Okay, so that's our first easy point. Our next easy point is actually C. It's actually pretty easy to do. Because if I look at my equation here, equivalence means the same number of moles of each of them. Okay, so if I have a look at it, we've got 0.5 moles per litre of sodium hydroxide, and we've got 0.25 moles per litre of ethanoic acid. What's the ratio between those two concentrations? 2 to 1. So I'm going to need half as much, and I use that word carefully, half as much, so half as many moles of half as much in volume. I mean, half the volume of that to have the same number of moles as 20 mils of this, aren't I? So if you want to do it the slow way, the number of moles of ethanoic acid, N equals CV, will be 20 over 1,000 to get it into litres, times 0.25. All right. So that's, I think, off the top of my head, 5 times 10 to the negative. No, brain's not working. 5 times 10 to the negative 3, I think. Then, to find the volume of this, then I just rearrange from our little triangle, N equals CV. Let's put the wrong one up there. So if I want to find volume, I go number of moles divided by concentration. And if I do that, I get 0.0100. So what's that in millilitres? What's that in mils? 0.0100. Not quite. 10. Okay, so half the volume required. So I can now put in 10 mils here. I don't need the unit because I put it in my axis. I can also get the volume here. And I'll give you the proof of that later if you want to see it. I won't do that on the video. But at this particular point, it's half of C. It's what we call a half equivalence point. Well, actually, in that case, it should be how many mils? Perfect. So I can put 5.0 mils in that one. So far I'm doing pretty well, actually. Now, the nice thing here is, there's a little rule about this. The pH at B is a certain certain special number. As I say, I'll give you the proof for that later on. At the half equivalence point, though, the concentration of ethanoic acid is equivalent to the concentration of the ethanoate ion. What do we call this? Where you've got an acid and its conjugate base in similar, and in this case equal, concentrations. Buffer. Great. Now in this case, this is a special one where they're exactly equal. So that means that the pH at this is equal to the pKa. And the pKa, because again I've used ethanoic acid, is 4.76. So I can put that number there. If I have my general shape correct, and I have those points on my graph, I'm going to get achieved for that. Alright, that's the stuff we expect you to be able to do pretty easily. The concentration of the strong base, therefore the pH of that base, so you know what it's heading towards. The buffer region, which is the half equivalence point, and the pKa, and the equivalence point volume, so using this NCV triangle, or using mole concentration ratios. Alright, so see that that's twice the concentration, so it needs half the volume to be equivalent. Right, now we get to the merit stuff. The merit stuff is doing A, and actually it's not that hard. We've done this a million times. What is present at A? So the moment before any base is added, what is present there? Just the acid. And what's so special about this acid? I'll rephrase it. So it's weak, fantastic. So to do A, you just need to do the calculation for a weak acid. So for this one here, our initial pH, we are just going to go C8, we're going to do the equation because, as you know, I love starting with these. This one is equilibrium because there's nothing else in there. So we get our ethanoate ion and hydronium ion. Because it's not a buffer, it's just an acid, we can assume that these two are in the same concentration. And we can assume that this one, because it's weak, is still going to be 0.250 moles per litre. So then we can do a Ka expression. And I'm sorry, I'm going to summarise it straight away to be hydronium squared, because we're going to assume these two are the same. And hydronium gives me pH over the concentration of the acid. So rearranging that, the hydronium ion concentration is going to be the square root of 10 to the negative 4.76, so that's our Ka, times 0.25, because that's our concentration. So I'm going to do that quickly. and I get 2.08 times 10 to the negative 3. So my concentration of hydronium, hope that's on video, is 2.08 times 10 to the negative 3 moles per litre. Then I do the negative log of that, because that's hydronium. So to find pH, I do the negative log of that answer there. Don't take it out of your calculator, by the way. Don't retype it into your calculator as that. Keep it in your calculator. Don't round it off yet. The negative log of my answer is 2.68. Alright, so now I've got this value here. And you'll notice, I mean, this is definitely not to scale. Whoops, let's just get that H a bit more clear. This is definitely not to scale. That's not what we're checking, that everything's to scale. Alright, if we're just sketching. However, if they do give you grid paper, then I suggest not putting that in until you've calculated it. And if you think calculating the pH of a weak acid is beyond you, then just, if you're not sure, put it around 3. Okay? And you'll be close enough. Alright? To get your general shape correct. 3 would be fine. Okay? I think you all should have the ability to do that though. Alright? Because that's our merit criteria and it's something we've done over and over and over again. Alright? So really, we've got our entire shape correct. If you did do it to scale, then you can actually estimate this pH very easily. You take the middle of the steepest bit, track it across, and you'll get your pH off your y-axis. There is, however, a way to calculate it, but I'm going to do that in another video. Alright? As I say, if it's done to scale, you will get this pretty close. And I suggest, even before you calculate it, have a look at what it is to get an estimate, to see if your final answer is at least close. It's nice to know that you're on the right track when you do the excellence question from your graph. So if it's, let's say this came up as, I'm guessing off the top of my head here, let's say it came up as 9.2 on our graph, and you get an answer that's 10.6 in the calculation, you can be pretty sure that your calculation's wrong, because everything else was correct. So you go back over your calculation. Right, but what I do want to go through is the importance of this. Let's say, for argument's sake, it did hit at 9.2. That means that an indicator that changes colour at a pH of about 7 is not going to be much use to you. So something like litmus solution or something like that is going to be no use. Because it would change around about here. And that's too far before the equivalence point. So it would mean your calculations for working out concentrations of unknowns will let me completely wrong. So what we have to do is choose an indicator which has a pKa in this absolute steepest part here. So you get quite a big range of pHs, but you need to have an indicator with a pKa, because indicators themselves are weak acids. One colour is the weak acid and one colour is the conjugate base. So phenolphthalein, which is the one you would use for this because its pKa is around about 9, its acid version, as it were, is going to be colourless. And then when you hit 9, you'll see a little bit of pink because you get the acid and the base present in equal concentrations. So we choose an indicator with a pKa around this. Oops. So if you look at the area I've dashed off, the difference for colour change is going to be so subtle, it's going to be a drop or two. Well, that's not going to make a difference in a burette. So you need your indicator pKa needs to be in this pH range. So in there. So you get quite a wide range. Alright? So even if you were just to estimate your pH for your equivalence point, you could still then estimate which indicator is the best one and justify it. The hardest thing in a titration curve like this one here is to find E, so the pH of the equivalence point. So the first thing to consider in this is that all of the acid has reactants. That's that equation you can see there. The big step that costs people is usually this one here, where we have to consider that there's 10 mils of the base, 20 mils of the acid. We found that from our graph. So therefore we've got 30 mils of the conjugate base. The number of moles stays the same because that's what equivalence point means, the same amount. So that means we can use this equation here to calculate the concentration of the conjugate base that's being made at the equivalence point. But because there is a weak base present, it will go on to partially dissociate, as shown by this equation here. Because hydroxide is being made, it's going to be a Kb expression. So we're going to make a couple of assumptions. One is that the concentration of the acid being made and the, sorry, I put hydronium there, it's meant to be hydroxide, are going to be the same. The other thing is that the concentration of the ethanoate ion is going to stay at the original value. We can also calculate the Kb quite easily from the Ka given in the question. So that gives us this expression here. The hydroxides being equal to the square root of the Kb times the concentration of the base. And that gives us this value here, 9.79 times 10 to the negative 6. From that, we can calculate the hydronium ion concentration, 1.02 times 10 to the negative 9, then do the negative log of that, and we get our final answer. So really, it's just the same as calculating the pH of a weak base, but we need to remember that first step and account for the change in volume.